This talk is about tissue versus silicone. So I'd like to tell you a little bit about my thinking about how we build machines for deep learning today. So deep learning is a beautiful field that is moving very, very fast and starting to kind of permeate everything that we do, from recommending movies to watch, to kind of deciding which ads to show us, to trying to analyze data in biological sciences. And there's a lot of hardware and software being built for this, and I'd like to kind of reflect on this hardware and software, and what directions we're taking. And I'd like to do that, from the context of my experience, not so much my experience as a multi-core expert, which I've been doing for 30 years, but rather from the place where I've been in the last 6 or 7 years, which is essentially a field called connectomics, a field of neurobiology. So I'm going to start by kind of giving you a little bit of a feel of what I do now in the field of neurobiology, and then I will try to show you how what we know from neurobiology reflects on the directions we're taking with deep learning. And so that will be the talk. Cool. So here's a photo. Okay, it takes you about 1/100th of a second to determine, that this is Mount Fuji. Okay, if you've ever seen Mount Fuji, right? So this is Mount Fuji in 100th of a second. How do you do that? How do you recognize it so quickly, right? Well, you do it using your brain, right? Neural tissue. Something is going on in this neural tissue that enables you to actually do this kind of recognition of images extremely fast. What is this neural tissue? Well, many of you have probably heard. It's made out of neurons, right? And so what is a neuron? You've probably heard the term. Some of you probably might know what it is. But let me just kind of explain at a very high level what a neuron looks like, okay? So a neuron, right, is a cell that has one part called a dendrite, okay, or a dendritic arbor, okay, this whole area, okay, and okay, it has a kind of axon, okay, a piece that extends over possibly very long distances, and then kind of branches out again to an axonal, kind of a collection of axonal arbors. Okay, and this long axon is often covered with a kind of protective sheet, insulating sheet called myelin. Okay, so right down here. And what happens typically and this is one cell, a neuron is one cell. Here is its nucleus. Okay, and if you look at what happens in a neuron, okay, well, it has connections called synapses, which we'll talk about in a second. It has, hundreds and thousands of them. Okay, and it also has synapses at the edges of the axon. And typically, right, an electric signal, okay, arrives down the dendrites, and then it's summed up, and based on some kind of thresholding, it's decided whether or not to fire a message down the axon. Okay, so there's a decision based on some kind of threshold, and then boom, it fires and sends a message, an electric pulse down the axon and to the synapses along the axonal arbor. And these synapses send messages to the next neuron down the road. Okay? The field that I work in, called connectomics, is the field of mapping the connectivity of this type of neural tissue. Okay, and to do that at the level of individual synapses, so we can really see the connections and understand what the graph looks like. Okay, so each synapse in our brain is actually a chemical connection. Okay, so while I describe this as kind of electrical pulse going down the neuron, really what is happening is that the actual communication between neurons is done through these objects called vesicles that contain molecules of neurotransmitter that are spilled out into the connection into the synapse between one neuron and the next. Okay, and this is, of course, being a chemical process. It's not a very fast process. It's a slow process. So here's an image of a slice through a brain. And so why is it that it's so complicated to understand what brains do? I mean, right, it's been so many years and we're still trying to figure out what's going on, even though we're dedicating, hundreds of billions and even trillions of dollars of research. Okay? Well, let's try to understand the scale, okay, of our brain. So here's an image of a brain, and it's about 10 centimeters across, right? And if I look at it, right, you've probably seen these fMRI images of vision regions, balance regions, planning regions, right? Um, and at that level, this is one level of organization of the brain. Okay, but if you now look, at a small piece of this, right, an order of magnitude less, so 10x less, right? What do we see? Well, what we see is that we have gray matter and white matter. Gray matter are the bodies of the neurons, okay, the cell bodies and connections around them. And white matter are essentially axons going across your brain, okay, with myelin covering them. That's why it looks white. So the middle of your brain is just this enormous communication fabric. So if you will, I've got the connections at the edges and the communication lines going through the middle of your brain. That's what your brain looks like. Okay? Now, if I go down another factor of 10 into your brain, okay, what will I see? Well, what I see here is the dendritic arbor, okay, the incoming connections of one neuron, one pyramidal neuron, okay? And if I go down and look another factor of 10 in there, okay? What I'll see is one dendritic spine. Okay, this is like the mechanism for incoming communication, and each one of these spines, right, in the dendritic arbor has these little kind of bumps, right, these little spine that you see there, and those things, right, are actually where the synapses are, where I connect to other neurons. Okay, so if I go and look at an electron microscopy image of this, okay, so I'm down another factor of 10 with an electron microscope image, and what I see here, this is a slice through a dendritic spine, okay? And on the other side of this spine is an axon terminal. You see those little round shapes here? These are the vesicles that contain the neurotransmitter. And right, this whole thing, the axon terminal together with the dendritic spine, is what we call a synaptic connection. Okay? So this connection, right, is where chemicals, these little vesicles spill the chemical connection, the chemical agent, right, which is essentially a neurotransmitter, from the axon to the dendrite, signaling from one neuron to the next. Okay, so notice that I'm doing this at the level of at the level of an electron microscope. Why am I doing that? Why electron microscopy? Okay, well, because it's impossible to actually see these connections at the level of a light microscope. I can't really tell who's connected to who with a light microscopy, and so I've got to do this with an electron microscope. And if I think of one voxel, okay, one cubic voxel in an fMRI, these beautiful images that you see of brains lighting up, right? One pixel is a cubic millimeter, okay? And this pixel is 10,000 trillion times bigger, okay, than a pixel in the image that I showed you. Okay, To just understand the scale of these things, right? Your brain has about a quadrillion, okay, synapses, okay, and 100 billion neurons in it. So an incredible, massive thing, right? In terms of if this is a distributed system, imagine a distributed system of this kind of magnitude. Okay, so this is why it's so hard to kind of talk and understand what's going on in this system, right? When a system is of this size and this kind of complexity, we have a hard time understanding what it's doing. Okay, now, and we've built technology, we've been building technology to actually understand what brains do. The idea of actually getting images of neurons, right, is not kind of new. So even though connectomics, the field I'm in, is about kind of mapping these connections at the level of synapses, people have created images of neurons before, and maybe many of you have seen images of this type of that look like what I'm showing you here. This is an image created using the black reaction technique invented by a guy called Camilo Golgi in the end of the 19th century. Okay, and using this technique, okay, a guy called Ramon y Cajal, Santiago Ramon y Cajal, was actually able to create delicate and intricate maps, and pretty accurate, of what neurons would look like. And Cajal drew these beautiful maps, and he concluded, right, that a neuron is connected to another neuron using an axon, and there is a signal sent down. While at the same time, most people at that time, including Golgi himself, thought that your whole brain was one big cell. So there were not individual neurons, but just one big connected spaghetti. Okay. And in fact, right, um, you know, uh, what kind of you see here, this beautiful image that Cajal is drawing, right, is showing neurons, but it's missing, most of the dense structure of what's going on here. Now, but it is beautiful in itself that he got the idea that these messages are being sent, down the axon and so on. And of course, Cajal and Golgi both won the Nobel Prize in 1900, and they each spent their whole Golgi spent his whole Nobel Prize speech just explaining why Cajal was wrong, and it was one big spaghetti. But it turned out that Cajal was right. And in fact, in the 1950s, with the invention of the electron microscope, we actually now know how things are really connected. So that brings us to this day and age, okay? And the issue is that, this image that I show you here that Cajal could draw was great, but right, it's very sparse, okay? How many neurons are really in this volume that's being described here? We only see individual ones, but the question is, what happens with all the others? And what are all the connections? Okay? So to kind of answer this question, okay, modern science is trying to use electron microscopy in a more sophisticated way, and this is where my work comes in. So what I'm showing you here is an image, right, of a microtome. On this, this microtome goes up and down, and what I have here is a tiny block of mouse brain, and this microtome goes up and down on this kind of diamond knife sitting over a bed of water, and we slice the brain and put it on tape. So what we get is essentially this brain on tape, okay? Miles and miles of kind of sliced little tiny slivers of brain, all sitting on tape. And this is my colleague Jeff Lichtman, okay, with the microscope that actually takes images of these little tiny slices. And this image is just intended to show you how short Jeff is. Anyway, with 61 beams, this is a very powerful microscope, and it goes over these. We take these slices, put the tape down on plates, feed them into the microscope. Each little tiny dot that you see here is a slice of brain. And it looks something like this when you look at it with a light microscope. You can see some images of cells, but it's very hard to make out anything else. And then, if you look at a region like this, right, and you take out and you kind of take a whole piece of mouse brain and you slice it up, you get 10,000 little pieces like that, each slice, being a slice through this brain. And if you took these 10,000 pieces and put them together, you'd get a block of brain, about 100 terabytes in size. Okay, so 100 terabyte block of brain, in this case thalamus. Now, right, what is the size of this thing? If this is a penny, that's the size of this 100 terabytes. Okay, and so in this grain of salt, and like a grain of salt, let's say, that is a cubic millimeter in size, you would have 100,000 neurons and about 1 billion synapses. Okay, so unlike the images that you saw of the pictures that Kahal drew that were very sparse, this block is extremely dense, okay, in terms of the number of neurons in it. Okay, and so if we take a slice like this and we try to kind of color it, to do a reconstruction, so this is a slice through the brain, okay? And if I try to color the individual neurons here, okay, then try to do a reconstruction of the slices into actual three-dimensional neuronal structures, okay, I can do that using machine learning techniques. And this is an algorithm that one of my brilliant postdoctoral students, Yaron Meirovich, invented. It's an algorithm that tracks through the slices of a brain. It tracks a neuron. So you can see the membranes in red, and you can see this kind of blue or purple image of the neuron, and the machine learning algorithm just tracks through this image of a brain, this neuron, it's actually an axon. It tracks this axon through slice after slice after slice of brain, okay, enabling us to kind of do a reconstruction of what this axon looks like. Okay, and what it's doing is mimicking what people would do by hand, but with a machine. And you can imagine the amount of compute that goes into this and the kind of machine learning algorithm that you actually need in order to do this kind of work. And so I got completely involved in machine learning in order to actually figure out how to track these neurons inside the tissue so that we can do the reconstruction. And the goal of this reconstruction, okay, is to actually be able to show you images like this. Here's an image, okay, created in the Lichtman lab of, two basically dendrites. So these are tiny, tiny little slivers. This thing is a 10,000th the size of that grain of salt that I showed you before, okay? So what you see here is one apical dendrite and another apical dendrite, a red and a green one. And, they look like pretty nice sitting in space, but in your brain, they're not sitting by themselves here. Okay, so I'm sorry. So what you see here, each one where you see the yellow pointer, this is actually one of those dendritic spines, right, that connects to another neuron. Okay, but here are all the dendrites that go through the same volume. Okay, so this dendrite is not alone. Inside that little sliver of brain are so many other dendrites. Okay, and and here are all the axons that go through this volume. Okay, and here are all the glia cells, the support cells in this volume. And together, this is what it looks like. So it doesn't look like those images that you saw from Kahal and Golgi, okay? It's really a very, very dense kind of thing, okay? And this density is what makes us think of the brain as this enormous computing machine that has endless amount of compute, and we build whole theories around this massive computing device that enables us to recognize Mount Fuji in 1/10 of a second. Okay? So by the way, this thing is 100,000th of the grain of salt. Okay, so this kind of crazy brain image that we have, okay, is what we carry into the world of machine learning. And people, when they think about, okay, what are we going to do when we actually now try to mimic these algorithms in our brains and do that, right, in the context of our computers, so that we can actually build machine learning algorithms. Maybe we're not trying to build a machine learning algorithm to mimic a brain, but we're trying to build a machine learning algorithm to recommend ads, to identify, to track neurons and things like that. So there are endless number of applications for this thing. Okay, and it happened to be right that when people started working on actually running machine learning algorithms, the breakthrough happened when people started using GPUs, graphics processing units, to actually run the machine learning algorithms. What it turned out to be that that actually GPUs, graphic processing units, have a really great amount of parallelism, okay, which kind of fits with what we think about when we think about brains, right? So a GPU has 5,000 cores, and it has about 16 to 32 gigs of memory, right? High bandwidth memory. This is memory that allows you to be connected to the cores. And to run a machine learning algorithm, right, you take whatever image it is you're running on and a description of the neural network, you put it into the shared memory, and then with the 5,000 cores, you're able to apply 100 teraops of kind of compute to it and run this network. Okay, both train it and do kind of inferencing on it. Okay, and the fact that you were able to apply this kind of compute with a GPU, and the amount of parallelism that it has with its 5,000 cores, essentially kind of brought us to a place where people were kind of enthusiastic. Wow, this enables me to actually run the algorithms efficiently, and the sky is the limit. And in fact, machine learning has been permeating and taking over a lot of parts of our computing landscape. The idea that people have in their heads, right, is this is all about throughput computing, meaning, oh, like I got to have this massive parallelism and this massive amount of compute, right, because that's what our brains do. Okay, and there are more than 70 different startups joining NVIDIA and Google and Intel in providing special hardware for running machine learning algorithms, GPUs, TPUs, and so on. This is Google's TPU Pod, right? What Google says is 100 petaflops of machine learning power. So they take hundreds of GPUs and TPUs and connect them together with cooling, with a massive cooling system. And this, 100 petaflop, right, is the image of where brains are going to go. Okay. So what I'd like to do is have a stop for a second and question this, okay? And ask ourselves, is this really true? Okay, and here I'm going to use a little bit of the kind of knowledge that neurobiologists have and try to apply it, to the compute of neural networks. And and again, I'm just going to do it based on the same path of biological inspiration, where where people think of the neurons in a neural network, in artificial neural networks, as inspired by the neurons in our brain. So let's look at the amount of compute in a brain. Okay, actually, in your cortex, in human cortex. Well, in the cortex itself, there are about 16 billion neurons. Okay, and a cortical neuron, just from energy considerations, we know that a cortical neuron spikes every 0.16 times per second. Okay, so this is the frequency of firing in your brain. And each neuron, this is from looking at images of neuronal connections in the brain, has about 7,000 synapses. Okay. Now, 7,000 synapses, how many other neurons does this mean one neuron is connected to if it has 7,000 synapses? 700 or 70 or 7,000, right? Well, it's not an easy question. We haven't actually settled it yet, but connectomics can help figure this out. What we do know, and here is an image that I'm showing you. Here is an image, right, um, of essentially a dendrite in green, right? And you can see here, you can see these kind of dendritic, spikes here in each one, right? And you can see, right, an axon in blue, right? And you can see the connections. So this axon, when it connects to this, dendrite of some neuron. So this is an axon from one neuron connecting with a dendrite of another neuron. And you can see that when it connects, it doesn't connect in one place, but in many places. So in this case, 5 different connections. Each one of these is a synapse, right? Well, what does this tell us? Well, it tells us that if you have 7,000 synapses, then you probably don't have 7,000 connections to other neurons. Maybe it's only 70, but let's just assume that it's 700. So I'm going to assume that you have 700 connections for every neuron in your cortex, okay? What does that tell us? Well, 16 billion neurons times 0.16 firing rate per second times 700 other synapses or connections to other neurons means that if I think of every connection as firing when my neuron fires, 700 of these fire when my neuron fires, I have about, 2 trillion operations per second. That's what my brain is generating. What's 2 trillion operations per second? Well, 2 trillion operations per second is less than what an iPhone does. Okay? So your brain, your cortex, when you're thinking, when you're firing, when you're looking at things, okay, it does less than a cell phone of compute. Okay? So it is 5 to 6 orders of magnitude less compute than the TPU pod. Okay? If the TPU pod, is our image of a brain, then it's 5 to 6 orders of magnitude, right? Too much compute relative to what our brain does. Let's just pick a thing that your brain does, like image recognition, like that image of Mount Fuji that I showed you. Okay? What's the amount of compute that takes? Okay? Well, um, you know, an image a typical image that we feed a neural network, 224 by 224, is about 500,000 pixels. When we run an image like that of 224 times 224 through a typical neural network, it's about 20 to 30 billion operations to do the computation, right? So, that, kind of that's the cost, right, that I take. So for 0.5 million pixels, it takes me about 20 to 30 billion operations. The human iris, okay, an image in your iris, right, is about 2000x more pixels. Okay, so a neural network would take about 40 trillion operations to do an image. Okay, if I wanted to process an image the way your brain does, it would take me about 40 trillion operations. Now, we recognize an image in about 13 milliseconds. So even if you use the whole cortex, okay, even if you use the whole cortex, right, then, 2 trillion times, 0.13 firings per second times, is about 20 billion operations per image. Okay, so your brain does 20 billion operations to recognize the image, and even if you use your whole brain, right? Whereas the neural network would take 40 trillion. So your brain is 3 to 4 orders of magnitude more efficient, okay, in terms of compute relative to the neural networks and the hardware that we have today. What about memory size? Okay, well, the human cortex is about 300 trillion synapses. Okay, if that's an edge in my graph, right, then to kind of hold the connectome graph of your cortex, okay, and let's say that I just use 4 bytes for every for every connection, right, for every edge, right, is about 1.2 petabytes. So a petabyte of graph, okay? So, compare that with a typical GPU or TPU or one of these hardware accelerators that has 16 to 32 gigs of HBM memory. The new NVIDIA GPU, the A100, has 40 gigs. So on that order of magnitude of tens of gigs, right? So, compare that to a desktop that could have 1.4 terabytes, right? Or a server that can have these days, close to 100 terabytes, okay? So, this kind of size of the accelerator, the GPU memory is very small. In fact, right, if you think of the pod, the Google GPU TPU pod, its memory is 4 to 5 orders of magnitude too small. Okay, if it's supposed to hold the graph of your brain, it just can't do it. There's no hope. It's just too small. So what have I kind of been telling you? What is my kind of high level conclusion from what we know about brains that we've been looking at for the silicon that we're building to do machine learning? Well, what we're building, right, is a device with thousands of cores, okay, and about 16 to 32 gigs of memory. So it's a petaflop of compute, right? We aim for a petaflop of compute on a cell phone of memory. Okay, but what we really want, what we need, is a cell phone of compute on a petabyte of memory, right? Exactly the opposite of what we're building. And this is where the problem is. The problem is, okay, that we are going in the wrong direction. Okay, we should be building. Sure, sure. Oh, I'm sorry. I can move my face up. Is this good? Sorry for the audience. Yeah. Sorry, I was getting excited and sliding in my chair. Um, what I'm saying is, right, we're building the wrong thing. Okay, lots of flops on small memory is not what we want. We want lots of memory with small flops. Okay, and why are we doing this? Why are we building this? Well, because we don't know the graph. So it's typical thing. It's a typical thing in computer science, right? When we have a new paradigm and we don't know what to do, we apply compute to it and we try to build hardware for it. Okay, and there are many examples of this. Okay, and so what does it mean that we don't know the graph, right? Well, if we could, if these projects to map the brain actually go through and we kind of get an understanding of how this computation goes, we will learn a lot more. But right now we don't know, so we're applying this massive compute. But look, the beautiful thing that's happening here is that the field of machine learning is by itself learning how to develop better graphs and understand what the graphs look like. And here's an example. This is an example from May of 2019. Okay, what you're seeing here are the new these new networks from Google called efficient nets. And what you can see here is this is like a graph of millions of parameters, the size of your neural network, and this is the accuracy that you get along the y-axis. Okay, and here are all the famous neural networks that we kind of are used to, from ResNets to ResNext to Inception to AmoebaNet and so on, right? And you can see, right, that the best these networks manage to do is this kind of blue line, right? And here we have efficient nets, these new networks that achieve really high accuracy when they're very small and stay very small to achieve accuracy that is better than what we had before. Okay, so for example, if you look at efficient net B0, okay, which is the size of a tiny mobile net, right? It gives you the accuracy of ResNet, which is over here, which is much more accurate network. So I'm over here, but I'm in terms of size, but getting the accuracy that I would get here, okay? Um, Here's another example, EfficientNet B4, okay, which is the size of ResNet 50, right, but gives you the accuracy of AmoebaNet. Okay, so we're doing better, with a smaller, network that has a lot less compute, right? With a network that has a lot less compute, because we are understanding better what it is, okay, that we need to kind of design, what the design of the network is. And this better understanding of a more efficient network allows us to very easily compete with those big graphic processors with lots of flops that we've been building. So, for example, if you run EfficientNet B0, okay, on an NVIDIA V100 GPU, their most powerful GPU, okay, and you run, this is, by the way, these are graphs of an execution that I do. I'm running this through the runtime of the Neural Magic runtime, which is the runtime of the startup that I have. But you could try to run this through other runtimes and get not the same performance, but you would get interesting results on this. But for Neural Magic, right, what you can see here is we're running and we're comparing this on AWS. And the reason I'm comparing this on AWS with costs is just because people typically check what the size of your machine is and what the amount of power you use is, and so on. So this is all kind of on AWS. This all goes into the price. And so when I say that a GPU is $3 an hour and a 4-core CPU is $0.34 an hour, that says this is everything, the power and the cost of buying it and everything together. And what you can see here is this, that here is at batch size 1, when I put one image at a time through my network, you can see the V100 is just not competitive with a 4-core CPU that costs a tenth of the price. Okay, and if I look at good, yeah, and the throughput, and here again is batch 64. Okay, and you can see that the V100, right, compared to a 24-core CPU running the Neural Magic inference engine, is just about the same, right? And you can get, instead of for the same amount of money that a GPU costs, you can take and buy on Amazon 9 4-core CPUs, and you'll be twice the performance. Okay, so this says something about what happens when I have an efficient network, right? And here's another example. This is a bigger EfficientNet. This is EfficientNet before, and again you can see the V100 is not performing as well as a 24-core. So this time it's not a 4-core. This is a bigger network. You need a bit more compute, but again it's competitive. Yeah. So the fact that I can do this, that I can run, on a CPU and compete with these accelerators, with the GPUs, what's going on here? What does this tell us about the bigger picture, okay, of the future of hardware and software? Okay, well, here's my take on it, and this is why I think down the road, we need to change, right, the way we are approaching the design of these hardware accelerators and the software that runs on them. So the first thing to observe is this, like there's this myth, okay, which is, machine learning is a throughput problem. CPUs cannot solve this problem. We need the massive parallelism and the enormous compute capabilities of these accelerators, okay? So is this really true? Do we really need massive parallelism, okay, to run these networks? Well, why is it that our brain has massive parallelism? Well, if you think about it, if you were going to build, a system that had to do 1 billion instructions per second, and the units that were doing your instructions were made out of, a chemical connection, and you had to get 1 billion of those chemical connections to work, to fire in a second, then you need parallelism. You need, 1 billion synapses to get 1 billion operations. Okay? But, a modern processor can deliver 10 billion operations even sequentially. You don't need, 10 billion modern processors to get to 10 billion operations. You just need one. So what I'm saying is, if I need a certain amount of flops to run something, okay, then I don't necessarily need these flops in parallel. I just need to have those flops. So the idea of parallelism in the brain, has inspired parallelism in neural networks, but nobody says this is really true. Nobody's kind of there. It seems like as long as I can generate enough flops, I can do the computation, and I don't care if these flops are coming in parallel or in sequence. Okay. And what is it about so if it's not the flops, what is it about neural tissue, okay, that makes its computation really great? Okay. Well, for one thing, it's extremely sparse. Okay. You saw how much compute it takes, your brain to recognize an image. I have an enormous graph, but it's firing very infrequently. Okay. And it has an enormous level of locality of reference. So one neuron fires into the next neighboring neuron, into the next neighboring neuron, into the next neighboring neuron. So your neural tissue is using sparsity and it's using locality of reference. Okay. And those are the properties that I need, not necessarily the massive parallelism. Okay. And that's what I want you to take away from this, that your brain tells us, okay, be sparse. Be local in your references, and you will be mimicking how the brain computes. And so how do we do this mimicking? Well, okay, today, right, the best thing we can do is to do it on CPUs. I'm not saying this is where we'll be in the future, but currently, the best way to get sparsity and locality of reference is on a CPU. And what I mean by that? Well, here's what you do on a CPU to utilize sparsity and locality of reference. Okay, so let's look at what a computation on a CPU looks like versus a GPU. So on the left is a typical way in which I run, a neural network through a hardware accelerator. So I have, a hardware accelerator like a GPU has thousands of tiny cores, and it has, a small amount of cache for each core, and it has an enormous, bandwidth to memory. So tiny cores, lots of parallelism, enormous bandwidth to memory. A CPU has few cores, powerful cores, but a few of them, not that much parallelism among the cores, right? It has enormous caches relative to the GPU, okay? And it has very slow bandwidth to memory. So on the hardware accelerator, the breakthrough for machine learning that happened was that it turned out people discovered that they could run through this network that has, many, many layers and multiple nodes of compute in each layer. They could throw this kind of each layer on the thousands of cores and in parallel apply all the compute to them. And then so I bring the data and the network description into the tiny GPU cache. I do the computation very quickly in parallel, and I spill it out, and I utilize the parallelism to apply this compute. And I do that again and again and again, layer after layer, synchronously through the network. That is the way a GPU executes a neural network. Okay? Now, if you were to try to execute this on a CPU, the same approach, which is what people do, okay, what do you get? Well, what you get is a disaster, okay? Because First of all, a CPU has less compute than a GPU typically, and it has, in a sense, less parallelism, right? And, right, it has, and this is the most important thing, it has terrible bandwidth to memory, okay? Maybe 10x less of the bandwidth of even a commodity GPU that you will buy today. Okay, so with poor bandwidth to memory and with less compute capabilities, running on a CPU the same way you run on a GPU is why NVIDIA is a $100 billion company. Okay, they figured it out, right? This is the right way to run a neural network in hardware, and while the CPU guys are running it the wrong way. Well, okay, but what you can do on a CPU is learn from the brain. Okay, so the first thing you can do is actually prune the network, and we know how to do that. In fact, in our brains, right, when a child is up to 2 years old, you are always adding synapses, and then at age 2 and on, you're pruning. So essentially, this kind of idea of pruning comes from nature. It happens in nature also. And what we find with neural networks is that we can prune them and still preserve the accuracy. And, at times lose a little bit, at times actually pruning actually improves accuracy. But the idea is once I prune it, I have reduced the amount of compute. Okay? But when I reduce the amount of compute, what happens now is that I take a computation that was compute bound, and now I've turned it to be memory bound, right? And so the next step, and this is what you need to do, and this is what Neural Magic, my company, does. Excuse the dog. 1 second, excuse me. Can you get it away? Yeah, thanks. This is life in Corona, right? You have a dog in the middle of the lecture. So what we do is you execute the neural network, not the layer after layer, but depth-wise. Okay, so we have figured out a way, and this can be done very efficiently, of running the neural network depth-wise inside the caches of the CPU. And the CPU has large caches, so you can keep a lot of the compute inside the cache, and from layer to layer to layer, just execute that piece inside, the CPU's cache. Now, again, if parallelism was necessary, then you couldn't be able to do this. But it turns out that you can actually do that. That as long as you have sufficient compute to execute the sparse neural network that is actually mostly memory bound, you can actually get great performance. And when I say great performance, here's an example. ResNet 50, which is a classical benchmark for machine learning algorithms. Here's what a sparse ResNet 50 execution looked like, right? A V100, right, that costs $3 is less effective, than a 24-core CPU that costs $2. Okay, at batch size 1, and it's about the same at as a 24-core CPU at batch size 64, which is a classical batch. The bigger the batch size, the better for the GPUs. They run with large batch sizes. But if you took 9 4-core CPUs, you would be 1.5x or more over the GPU doing this. Okay, so what I'm kind of saying is, if you sparsify your network and you know how to run it using locality of reference in the CPU, then you get performance. And this is true, okay, on Intel machines across multiple networks. Here are examples, of ResNets and MobileNets and SSDs and Inception, all these networks, and you can see that essentially, right, if you do the right algorithm, you can compete with the GPU. And if you have the wrong algorithm, then the performance is not that great. But you have to figure out how to use this locality of reference and how to use sparsity. And here's an example of batch 64. This is on an AMD machine, not just Intel, also AMD machines, pretty much the same. And here's batch 480. This is a batch size of 480, which should be really great for the GPU, okay? What happens when you do a batch size of 480? Look at this, okay? Batch 480, you can see right? That actually I see the TPU T4, here in these three networks, but at batch 480, the SSDs and the VGG19 actually crash out of the memory of the GPU. So those 16 gigs cannot hold batch 480 for some subset of networks. So we're running into the real story here that, accelerators deliver a lot of flops, but if you have sparsity, you can eliminate these flops and you can eliminate the problem that is generated by the fact that these accelerators have tiny memories in order to give you all those flops. So, if you want to think about the future of hardware for machine learning, so, what I'm saying is kind of today, use the CPU's large caches and large cache hierarchy, right? To run neural networks by using sparsity and using the fact that you can execute inside the caches in a sophisticated way. Okay? And tomorrow, in the future, let's build the right hardware. Okay, what is this right hardware? The right hardware is not a petaflop of compute on a cell phone of memory. The right hardware is to build memory, okay, that can be accessed in a graph-oriented way. So you can think of a special kind of CPU that has a terabyte of memory, and it is connected in a way, and you change your prefetching algorithm so that it's different from what we do today. Today, the way we do prefetching in a CPU is based on the idea that what I'm looking at is a graph or a matrix, right? So I always prefetch the next block based on down the what I believe to be the vector or matrix that I'm looking at. Right? And if I could prefetch in a more sophisticated way, in a graph-oriented way, this might be the way to actually enable me to have, very little compute and a lot of kind of performance for machine learning algorithms, because what I want to do really is run enormous graphs, okay? And as those graphs get bigger, this idea of using the cache hierarchy and using memory is going to dominate, okay, the whole kind of flops oriented world that we are in right now. And so, with that, I'm just going to say, together with all this, neurobiology is going to try to move forward. And what I do in my kind of research is try to learn the graph, because I think, the graph alone will not save us, but really, if we are going to understand how to build better deep learning algorithms, then understanding what the graphs in our brains do is a way to improve our abilities. And with that, I thank you.
Yes, thank you very much for your talk. It was really exciting, and I hope our audience will have a lot of questions. But for first, let me ask you. You've been talking just a moment ago about prefetching using the graph algorithms. Is there any algorithms which are already capable of doing this prefetch? Because I've spent some time working with graphs, and I know that it's pretty hard to distribute graph data in a way that locality holds.
Right. So the thing that is making it hard for you is that you don't know what the graph looks like. But imagine, right, that I actually had information ahead of time, a lot of information of what the graph structure was, and that this graph structure was very kind of had a kind of a modularity, right? Which we think is what's happening in your brain. Okay, so imagine that there is a modularity to this graph structure. Then I can design in my hardware a prefetching algorithm, that will mimic and best optimize the specific layout that that I know exists there. Right, and that's where I think the big hope is. Not so much from being able to execute, to prefetch on arbitrary graphs, but rather specific graphs whose structure I know.
And during your research of the brain structure, is the graph in the brain are actually localized? So the axons, how long can they be? So is the brain graph actually limited to some space?
So so in your brain, right? You have a very thin layer of about up to 6 millimeters of kind of gray matter that is kind of sitting around the edges of your brain, and then the whole center of your brain is mostly axons going across. So the distances that these axons travel is about from one edge of your brain to the next, right?
Mm-hmm.
But it is also a single neuron that goes from your brain down to your leg. That's one neuron, okay? And so neurons can be very, very long if you need them to. And of course, inside the brain of a blue whale, axons are much, much longer. Okay, so there really isn't that much of a limitation on the length of the axons and how long they can travel.
So then it means that in the brain, the graph structure is encoded in the hardware itself. So is it possible then to mimic this thing in a software way? So even
Yes,
if we
I
know
think
the
so. I
graph
think this is.
structure.
Yeah, I think so. I think look, here we are, we're doing it with neural networks. It's right now these are small networks, right? Right now the networks are small, but in a lot of places we're building, hardware and software that directly mimics these graphs. And I think that, think of it like this, right? Even though a neuron is firing with a chemical process and so on, all this computation can probably, these are all Turing machines, right? Whether I recognize an image using a computer or I recognize an image using your brain, it's the same computation that is happening on either device, the biological device or the physical device. And so I think now it's just a matter of efficiency. Do I find the optimal algorithm for this? And I think the optimal algorithm can be a combination of the right hardware and the right software tailored to the specific tasks that I want to do, right? And if I want to build a recommendation system, I would probably not build the algorithm the way your brain is, because I don't think you would be a very good recommendation system. But if I was doing image recognition, your brain probably is the right algorithm, right? So we can just pick the algorithm and mimic it in software. I think this is totally doable.
The right algorithm. Okay, we have a few questions also in the chat. I'll tell them. The first question is about the iPhone power. According to the specs, iPhone should have 5 billion operation per second, not trillions. Or how we got to the 5 trillion operation per second on an iPhone?
Did I say 5 trillion? I'm sorry. Let me see. 5 trillion? Where is that? It's a mistake. In any case, it's very small.
Yes, it's iPhone. It's not big, fortunately.
No, so I think no, I don't think this is true. I don't think so. I have to check. I think that if you look at the GPU inside an iPhone, it does 5 trillion ops per second. This is again This is to be
So you
checked. I
mean
can't check it right now.
uh,
Inside an iPhone, there is a GPU. It does 5 trillion ops per second.
okay,
This
so
is
it's
off
not about the
the.
main processor, it's about the
No, not
GPU
at
on top
all.
of it.
Right.
Well,
The
that's
point is
fine.
that it's a very the point is it's a very small computing device. Okay, it doesn't have to be a farm of processors. Is my point. Yeah.
Yes, I think we
By the
got it.
way, and let me just say, and I just want to say one more thing. Just since we're talking orders of magnitude, I picked 700 here. Most likely, the number of connections is 70. So it's an order of when you're talking about something that is, I'm talking about 5 or 6 orders of magnitude less compute. Okay, so it's 4 orders of magnitude less compute. I don't think that changes the basic idea. Thank you for the comment, right? But I think the basic idea here is that we don't need this much compute. Okay.
Yes, I think they got the idea. And we have also an interesting question. Is there a way to improve our brain, or can we only hope for avoiding to making it worse?
So, I have colleagues that work on little chips that you attach to a brain to connect them to neurons. This research is only at the very beginning, and today people are using this for very simple tasks, and a lot of the connections are just to to neurons in our peripheral system. But I see no reason why we would not have enhancement to our brain. And in fact, I think that it'll probably be a very sad world in the future if we don't have extensions to our brains, because you can imagine a world where I build an artificial brain that has 100x the capacity of ours, and I have to try to understand what it is thinking, without an additional piece of hardware. This computer to me would be like God. And I don't necessarily want that. So I think enhancing our capacity at the same time that we enhance that of the computing devices we use is a real thing that we will want in the future. And I'm sorry if everybody gets scared from this idea, but it's just a thought. It's just a thought. Just a thought. Yeah.
Yes, and it actually sounds reasonable. So we need to keep at the same level as the things we are creating. Otherwise, we might get into troubles. Um, and what about the utilization of our brain? Because there are a lot of hypotheses about how much of the real power of the brain are we using now? Is it the whole brain which is working, or just a small part of it, and we can do much better with the same brain?
So thank you for that question. So we don't know that much, but we know enough to understand that the way we use our brain is in a very sparse way. Okay, so when we have when you see when I said that your typical neuron fires every 0.16 milliseconds, right? That's the whole activity of your brain. So while the brain itself, while the cortex itself has tens of billions of neurons, only a small fraction of them are firing at any given moment. And this is what it's telling you. It's really telling you that this is about extremely sparse computation. Think of the graph, right? If I have 7,000 synapses, per neuron, and it's connected to 700 or 70 other neurons. While I have in my brain, 10 billion neurons, then the graph is extremely sparse, right? And the computation through the graph is extremely sparse. But most likely, right, I am using, over time, when I learn things, I'm using parts of this graph to build mechanisms for kind of fixing computations for different things that I know. So perhaps, and we don't know this. This is just this is just theory, right? Perhaps what's happening is that every time that I kind of have a new memory, I'm strengthening the synapses in a certain region, and next time that I see an image like Mount Fuji, I am firing through those regions. Okay, that's kind of what probably is happening in your brain. And the thing that we use most, right, to actually limit the computation, to lower it, is inhibition, which I haven't talked about at all. All my examples were of excitation in your brain, but there's a lot of inhibition going on. There's inhibitory neurons, and what inhibition does for you, right, is limit the context in which your brain is firing. So if I'm sitting in a room right now, right, I am not expecting an airplane to come through. So I'm not preparing myself from an airplane to go through the window. Okay, and that saves a lot of neurons in computation. And I think this kind of context is something that we are starting to understand and actually use, right? This thing called attention. We're using it in the context of neural networks today.
So the research which detects the low utilization of the brain, this might be inherent to the sparsity. So we use only a small part of the brain at a time because of the sparse computational structure, and it's kind of inherent property of the brain. And that's maybe even evolutionary efficient because we use less power.
That's right. We use a lot less power. Exactly. That's right. Yeah.
Okay, and I think the most inciting thing of the brain is not how it computes, but how it learns. During your research, do you have any hypothesis how actually the learning algorithms in the brain work?
Yeah, so this is a big area of research that we have very few answers. We do have a lot of experiments that show, and a theory that shows that synapses get strengthened with use, right? And that as synapses get stronger, right, this might be the form in which we remember things. But this can only be true for long-term memory, because if I just now, if I told you now, I told you about a Lincoln fish. You know Lincoln, the president of the United States, right?
Yes.
Well, if I told you there's a fish named after Lincoln, a Lincoln fish, right? Good. And if I ask you about the Lincoln fish 5 minutes from now, you will remember the Lincoln fish, right? But there's no time to make a synapse for that. Okay? So clearly your short-term memory is not just based on creating synapses. Okay? So most likely the short-term memory is some kind of active firing through the brain, while the long-term memory might be, preserved in the synaptic connections and in pruning them and so on. Okay, and to be truthful, we have a lot of theories and we have some experiments, indicating the path, but we don't really know the answers.
And then how long does it take to make a synapse? So if for 5 minutes is not enough, then how often are they made? Is it
No,
made,
so it's not so much that they're made. Yeah, so it's not so much that they're made, but that they're strengthened. And we have examples over hours and over days how synapses, when they are when a neuron is firing successfully, right? And there's a whole, I don't want to get into the whole kind of mechanics of it in chemistry, but there is this thing called the Hebbian principle, which many neurobiologists believe in, and other neurobiologists don't believe in. Neurobiology, unlike computer science, is not you can't decide that's the way it is and that's it. They don't sin in this way that we do, and so according to the Hebbian theory, it's the strengthening of the synapse synapses, and this happens over, it depends what type of synapse, but this can happen over hours and over days. So it's the strengthening and not so much the creation of synapses that is actually, we believe is involved in this process.
Great. Maybe one more question before we get to discussion zone about neuromagic. Can you say a few words? So how the magic works? So you showed us the excellent results on the CPU architecture for neural net inference. So is it neuromagic who does the network sparsification, or is it an algorithm to employ the already induced sparse networks?
Yeah, so Neural Magic has a tool which you use, which Neural Magic is about to open source for everybody. And this tool is a sparsification tool that you take a neural network, and what it does is it, in whatever framework you work in, either TensorFlow or PyTorch or Keras, it allows you, after you've finished the process, or you take a network that's pre-trained, after you've trained your network, then it runs you through a sparsification process where you prune and retrain several times. After which, you prune and retrain basically until you you prune the networks and recover the accuracy. You can prune ResNet to 87.5, like I showed. You can actually prune it even to 90% and preserve accuracy. It's just a matter of effort. So that's one part that you do. And then once you do that, Neural Magic specifically runs everything in the Onyx runtime. So there's an open source framework called Onyx, that it's the Open Neural Network Exchange, and so networks developed using PyTorch or Keras or PyTorch, right? Sorry, or TensorFlow, all can be transformed into the Onyx format, and the Onyx runtime runs these. And Neural Magic, okay, my startup, is a provider for Onyx. So if you get a neural network graph and you run it in the Onyx runtime, and you specify NVIDIA as the provider, then you can run on a GPU. And if you specify Neural Magic as a provider, then we run it on the same CPU that you actually started the computation in. So instead of sending parts of the neural network graph to a GPU to be computed because it's very compute heavy, right? We actually run it in the Neural Magic engine on the CPU in a very efficient way. And yes, the way we do that is kind of along the lines that I described in my talk. So we take the network that you sparsified using our tools, and then we run it by actually executing it in an efficient way.
So NeuroMagic is an open source framework which we can integrate into our train loop, and provide some sparsification of the network. And at the end, we get a network which works an order of magnitude faster than the normal network would be, because it sounds great.
Well, let me just say this. So Neural Magic's runtime is not open source. The tools for sparsifying are, and running in Onyx is open source, right? But in the same way that NVIDIA doesn't show you what the CUDA kernels look like on GPU, we don't show you what the CPU kernels look like. Okay, so so it's not open source in the sense that everybody keeps their their algorithms proprietary, but you can use it. Yes,
Great. Well, that sounds really great. Vasily joined us.
Vasily, I'm Vitaly.
Oh, Vitaly, sorry.
Yeah, no worries. I think the talk was really amazing, and we even had questions from their auditorium, which is quite nice. I didn't expect that. Thank you very much, Nir, for your precious talk. It was very interesting. Thank you, Dmitry, for monitoring the session and asking very nice questions. So I hope that somebody will join you into Zoom meeting. The link is somewhere below my finger. And I hope you at least you had fun right now, and I hope you all the best.
Yes, lots of fun. Yeah, thank you to everybody. That was lovely.
Thank you very
Thanks
much.
a lot.
Okay.
Okay.
Bye.
Okay. Bye-bye.
Thank you.
Bye-bye.